now recording. Okay. Let's start with the current slide. But before we get going on this, I wanted to go over one more announcement because I wanted everyone to hear this, and since we have one person not here, I wanted him to hear before he hears about it in the negative way. But y'all need to hear it too, but I know the three of you, at least on my sheet, have paid. So you're free from this, okay? But you may have friends who have not completed payment. Supposedly, I heard this Friday, that last evening sometime after business was over, they went through and removed all unpaid students from the rolls. I don't ever recall them doing that this early in the term before, but I think they're starting a new trend here, trying to get people to pay more quickly, okay? Now, if they knew that your financial aid was in progress but not in place yet, they may not have removed you. If they knew that you were on tuition management and that company was just holding things up for some reason, they may not have removed you. Unless you told them you were on a scholarship that was on the way in, they just probably recognized you as not paid, so they may have removed you. The point is, if someone was removed from the roll and they're planning to pay, has the plan in place and are in the process of doing it, they can contact them and they'll put you back on the roll. Okay? Y'all are on the roll, y'all are in good shape. But if you know of someone that fits that bill, tell them not to get panicked or discouraged. Let them know either financial services office or the cashier's office, the business office. Let them know where you are in the process. Well, just waiting for a check. As soon as it gets here, I'll pay. They may let you back in just on that promise. But please, this new technique of doing it is really screwy for us because every time they remove you from the roll, then we lose all the attendance. And then they put you back in the roll, we got to go back and put all your attendance back in again. So it's really not the best for us to see the administrators are doing it. They don't care what's best for us. I didn't say that, did I? Okay. Next, any question on anything we've covered so far? Okay, I did want to say this too. Apologies are still in order. I started work. In fact, I think I got your syllabus, if not completely updated, at least I got started on it. But I didn't get it on Blackboard yet. Okay? I did get your playlist set up on YouTube, but I don't have that connected to Blackboard yet. I got so much done, but I ran out of time before I got it all done. I have a little bit of time this afternoon. I'm hoping to be able to catch up on the rest of this stuff either this afternoon or tomorrow, okay? I don't have much time tomorrow. It may be Friday, but hopefully by next week, I'll have Blackboard completely set up. Sorry that it's not done yet. Okay. But, all right. Any questions on anything from syllabus, research paper, safety, or what we started doing in Chapter 2 last time? All right. No questions. Then we're on page 55 in 2.1. And again, the quality of the PowerPoints that come with the text, that's it. Well, you can't see it. Yeah, that's it. Little bitty thing, lots of white around it. So I'm going to expand on that, make it at least a little easier to read. Still, it's not the best use of the slide, but I can't expand it anymore. It only allows me to expand once. Okay. Now, 2.1 is talking about limits. We haven't gotten quite there yet. Rates of change, yeah, that's what we're beginning to talk about here. And tangent lines, that will come later, okay? But they're all related. So here's an example I know you're aware of. Whether you use this terminology or not, I'm not sure, but a change in position is equal to your velocity times time. And whether you thought of using that or not, you've done it. If you ever driven, say, to Tuscaloosa, okay, that's about a over an hour drive, approximately, okay? And if you travel about, let's just say, average about 70 miles an hour, it's less than 70 miles, right? To Tuscaloosa, or is it right around 70? From here, it's probably a little less. Maybe from Birmingham, it's about that. But you do that mentally every time you take a trip. You know how fast you're traveling, how long you're going to drive. You know about how many miles you're going to cover. Or if you know how many miles you want to cover, and you know about how fast you're going to drive, you can figure out how long it's going to take. Or, you know, there's several ways you can do this. This is a very common thing. A change of position is velocity times time. What does that have to do with a limit? Nothing yet. What does it have to do with the rate of change? Well, guess what, folks? A velocity is a rate of change. How do we define most velocities? Like if you're driving a car, what's your velocity? Give me an example. Okay, that's the correction. Yeah. Okay. Miles per hour. Miles in a given hour. That's the rate. How many miles do you go in a given time? And then guess what? Miles per hour times hours. Hours cancel out. That gives you change of position in miles. Yeah. We've done that. That's a rate. You do it all the time. Okay? Now, however, I gave the expressway as the example because you can get on the expressway, hit cruise control, and pretty much go unless there's an accident or traffic stoppage or something like that. Then you got to get out of cruise control. So that's with a constant velocity. I said your average velocity. But you know, most of the time when I'm driving, especially on city streets, I'm not driving at a constant velocity. I'm always changing. Well, then, this is a variable function. That could be a piecewise defined function. It could be anything like that. So if this is a variable function, then you have an equation here. Okay? And now we're talking about how far you travel with a rate here, change of time there. You know, you got a lot of different things going on. That's what calculus deals with. Change, changing, variable, you know, rates of change. Okay? If you use average velocity, which is what I gave, then you can use this formula just like it is. But if you're using instantaneous velocity, and that's a variable, then you got to deal with that. Now, how does tangent lines come into play? Okay? Maybe these will help. Now, number one, let me get my pen set up. I can't do the black pen because that was going to turn off my screencast-o-matic, so I'll use the dark purple, okay? But also what I want to do is blow this up. Boom, I blew it up, okay. All right. Now, what if you were at the Barber Race Course? I've never been there. Well, let's just imagine they have a circular course there, okay? I guess they might, okay? And here you are going around in circles. Sort of feels like trying to do register. No, I didn't say that. Okay, going around in circles, okay? If I ask you for velocity there, Richard started talking about direction, which is involved with velocity, okay? But also magnitude is involved. This could represent, if it had an arrow on one end or the other, this could represent your velocity. Say you just had that part with an arrow on it, that would be your direction at that instant, and that length would represent the magnitude, your speed, okay? But in the very next instant, you change direction. So now you'd be down this way, and then this way, and then that way. So this would be your tangent line, the tangent to the circle. That's what a tangent line is. It connects at one and only one point. And at that point, this could represent your velocity. So that's how tangent lines are connected with rates of change. Let's say that you're on a curve like this, not necessarily a circle. Let's say you're on any curving street out there. At any point on that you're there, if you are going that way or this way, you would use one or the other, and the tangent line would give you your instantaneous velocity at that point. A little bit later, you might be here or here. If you're going straight line, then your instantaneous velocity is probably your constant velocity. Could be. Okay? Now, would this be representing a tangent line? No, it crosses at one point. Didn't we say a tangent line crossed at one point? But that crosses, this one doesn't cross the curve. It's tangent to the curve, adjacent to the curve, but it doesn't cross. That is not a tangent line. That would be a tangent line at that point. It can't cross the curve. It has to be adjacent to the curve. Okay? Now, let's see. Yeah, here's somebody. Who in the world is this? Now, this is not the same picture as the one we have in the book, or in my book anyway. It almost looks the same, but it's not. Okay? Because here in the book, the guy's looking up, and here he's looking out.
Yeah.
But they're both Newton, okay? I don't know how they got. Maybe it's just a pantomime, you know.
Maybe it's a new. Well,
maybe
if
it's.
they went and did it this way, he would still be looking down.
It seems like it, so I don't know. But his leg looked the same, and the coat looks the same. I guess I don't know. Maybe they did get the camera right underneath them. Rodney's here, perfect attendance. All right, way to go.
Well, you like a bell we can ring.
Yes. All right. Rodney, if you'll see me just a moment after class, let me go over something I went over the rest of them with earlier. All right. And so it may be the same thing. You just take them from a different perspective, but it sure doesn't look. Looks like here he's looking up, there looking out. I don't know. But this is Sir Isaac Newton. Never mind what it is. It's the same statue, obviously. Okay? Now, why do they have Newton in here? He's the one who developed this stuff. Okay? I don't know this is for absolute certain. It may have been dealing with other things too, but I know that he had a friend, Johannes Kepler, who had done some amazing work with planetary motion, empirically, meaning he had the data and he was meticulous about analyzing that data, and he came up with these 3 laws of planetary motion that seemed to fit all the data he could get. And to this day, they still fit. But he couldn't say why it fit. It had some weird relationships in them, but they all panned out to be true. He asked his buddy Isaac Newton, why would this be? Now, I don't know if this is correctly put together, but the way I imagine it, and this could be way off, is that Newton had probably already been working with the concept of gravity, and he figured that had something to do with how the planets move. He had, in working with all the stuff, light, optics, all the things he was working with, gravity, motion in general, he found the mathematics at his hand that he could lay his hand on, that he could use, that he had studied, were inadequate to describe it. Because all they could do was average stuff. They couldn't do instantaneous stuff. So he came up with what he called fluxions, or something like that. I don't even know how to pronounce it. And it was the beginning of differential and then later integral calculus. And he, in developing the math, so he could develop the explanation for, I think it was Kepler's laws of motion. That's why we got calculus today. Thank you, Isaac, for providing this for us. Okay. And boy, it changed science. It changed history. It changed just about everything. Whole new mathematics and a whole new physics and a whole new understanding of the universe as we know it. And he isn't the last word. I mean, many people have done many things to modify, to expand, certainly calculus, even his physics, Einstein came along and introduced whole new areas that you could possibly have thought of because you didn't have the technology to. But yeah, other people changed. Boy, that one guy did more change than I think anyone else in the history. Okay? That's why his picture's here. Looks like a pretty nice guy, right?
Very inviting.
Huh?
Very inviting.
Very inviting. Very pleasant looking. He was, from what I understand, he was a pain in the neck. He fussed and fought with other scientists and others. A very insecure, fascinating character. Another guy came up with calculus also, using actually a little bit better notation, one that we use today. His name was Gottfried Leibniz, okay, from Germany. However, Newton was convinced because he had discussed his thinkings on it. Newton wouldn't publish until he was absolutely sure that no one could raise any questions and doubt him in anything. He wanted it absolutely nailed down perfect. He was a perfectionist. Leibniz came out with a form of calculus that didn't look like Newton's, but still had a lot of the characteristics. I mean, it was doing the same thing, using different notation, and he rushed to publish his before Newton did. And Newton was furious because Newton had been working literally decades on this thing, trying to make sure he had it perfectly in line before he published. And this guy published and had some of his stuff wrong, but there ensued for the rest of their lives, they fussed and fought with each other, claiming plagiarism, claiming stealing, I mean, just all sorts of stuff. So he wasn't the nicest of characters. He fussed and fought with others too. I don't think he ever did with Kepler, but he did with Robert Hooke, he did, and several others. Okay.
It's
Of
sad
course.
that even happened because they both, followed up of, their own versions of it's crazy. It's almost makes me wonder what would have happened if they worked together.
Right. Or even ignored each other and continued and didn't waste all that mental energy, physical energy, and everything else fussing and fighting and going on to do different things. They could have, who knows? Yeah, you're right. What if they had worked together? Who knows? But anyway, that's why Isaac Newton is done here. Because he had to talk about what's happening at that moment. Okay? Instantaneous velocity. That's differential calculus. Okay. Historical perspective. Another guy is mentioned here, Galileo, and of course Newton. Johannes Kepler is mentioned. Principia, which is Newton's incredible work, and did much more. There was also Alexander Pope, but he was just writing about him. So, guess what? This can't be your source for your paper. This can give you ideas for your paper, but you got to get your sources outside the book. Okay. Now.
Just out of curiosity, I was going to ask you something.
Yeah.
On that, instead of having to click and do zoom in, see if you can put both your fingertips on the mouse.
Okay.
And expand it, and see if that will zoom it in.
Okay, let's try it. Right there?
Yes. Both fingertips and expand.
Yeah.
Will that do it at all?
Nope.
No. Okay, I just wanted to
This
see.
This is
It
backwards.
works on mine, and I didn't.
But you don't have these slides.
I don't have those slides,
Right,
of course, but I'm just saying it's a lot easier.
Yeah, I know.
If you take it, anyway. So
Yeah.
I was just trying to help you out.
Yeah, this is archaic. Whoever did this was not very well versed in technology, I don't think. Anyway, okay. So let's get to what we mean by average velocity. We know what that is, don't you? You gave me a minute ago what the units were. What were they? Miles per hour. So what do you do? How do you get your average speed? You figure how many miles you traveled and how long it took. How many miles you traveled is what they call delta S. You started at one position, you ended at another position. The difference in that beginning. So let's say you were doing the Tuscaloosa, I don't know what their numbers are. Let's go the other way. Let's go out to Anniston, okay? I know in Birmingham, there's some mile marker in Birmingham that you can read off the side of the road. And in Anniston, there's another. And if you read the difference between the mile marker in Anniston and the mile marker in Birmingham, that's going to tell you how far you travel, right? So that's what the delta means, difference. Difference in mile marker 373 and 251, okay? The difference is how many miles you travel. Delta means difference. And this is over a time interval T0 to T1, that's your delta T. So let's say you started at 1202 and you got there at 255. Well, 1455. You subtract and you get your change of time. That's how long it took you. Okay? So delta S over delta T is how we've always done it. In fact, what does that seem a lot like? I think you probably use deltas in too. When you use slope of a line, what did you have then?
Rise over run.
Rise over run. Change of y over change of x. Delta y over delta x. You've done it since high school algebra probably, when you did slopes of lines. That's what we're dealing with here. Okay? So this is your average velocity. The change of your displacement, we'll call that S, over change of time. That gives you your average velocity. Okay? And this is your displacement at 255. Read that mile marker. Subtract from that what you were at 1202. That's your displacement here. The difference there is how many miles you travel over that time. That is changing. Miles per hour, the units fit. Miles in the numerator, hours in the denominator. Boy, makes sense, doesn't it? Okay? So that's one way to talk about average velocity. Change of position over a change of time, length of the time interval. Okay? They mentioned Galileo. This is supposedly, he came from a town in Italy named Pisa, not Pizza, but Pisa, P-I-S-A. And what does that have as a famous landmark? The Leaning Tower of Pisa. Now, whether he climbed the tower and dropped the rock, and supposedly this was an experiment he did. Now, I saw a cartoon once that had him on this side of the building, and he dropped it and bounced and bounced and bounced. He said, something's wrong here. But that, I don't think happened. Okay. But anyway, Galileo, by whatever means he did, see that he looks like an old Greek, doesn't he? Never mind, Italian. Okay. If he had his assistant down at the bottom, of course they didn't have stopwatches, so how he timed this, we don't know. But anyway, if you were maybe sand through an hourglass, I don't know. But anyway, I think I do know how he did this. He didn't use the Leaning Tower of Pisa. He rolled marbles up an inclined plane. That gave him longer to figure the time. He did the calculations, and he came up with the displacement as a function of time is 4.9 times the time elapsed squared, and that gave him the displacement in meters. Now, this is probably very similar to the formula that Galileo got empirically, just from doing his experiments. By the way, that was the beginning of the scientific method. He's the granddaddy of that. You know, he did experiments. He didn't just think about it. He actually did experiments. Okay? And he came up with a formula very close to this. Now, we know today, now, I bet you he wasn't using meters because metric system hadn't been developed at that time. But whatever he was using for the units, he came up with a formula that was similar to this. It would have had a different constant if he wasn't dealing in the metric system. But he came up with a formula like that. Okay? Now, today we know what that comes from. In other words, we've got an empirical formula. We can now tell you where that number 4.9 came from. Anyone have an idea? You should if you had physics.
Half of gravity.
half of the acceleration due to gravity in the metric system, that's 9.8, and half of 9.8 is 4.9. Of course, he didn't have that, but he came up with this concept.
That's so cool that
It really is.
they figured all this out.
Yeah. It really is. It's amazing. These guys, you have to think, okay? And they practiced it and did it, okay? So anyway, this was a formula, very famous, came up with by Galileo. That's why he's a possibility as a paper topic here. Now, in reality, he did it empirically. He measured, and he could not have done it to the intervals they give here. Galileo couldn't, because he didn't have anything that could measure time this precisely. But we can do this. We can look at the time interval over which something is happening. I don't have a clock that can give you this precision, but if you were to do it and calculate the average velocity from the formula we just had, okay? Remember what that formula was? Now, as soon as I go to write on this, it's going to shrink back, but no helping that. I think I'm already there. Okay, yeah. The formula we had was S of t is equal to 4.9 t squared. And this is measured in meters, okay? And we're using the velocity, average velocity, I'm going to call it V bar, to be change of S over change of t. Now, back in pre-calculus algebra, I think all of you had, right? We talked about difference quotients. That's exactly what that is. It's a difference. Change of S is change of difference between S2 and S1, and change of time T2 and T1, or T0 and T1, whatever you want to call it, okay? And if you did this, and if you were to plug in for your S2, this would be, I think the book calls it S1, so let's do it. S of T1 minus S of T0 divided by T1 minus T0. That's what they're using. And if you use these time intervals, and I can kind of imagine a clock that can measure that precisely. So if you plug in 0.81 for that and plug it into this, 4.9 times 0.81 squared. Got a calculator to do it. 4.9 times 0.81 squared. Times 0.81 squared minus 4.9 times 0.8 squared, that's 0.64 by the way, equal, but divide that by 0.01, and you get this? One more time.
Yep, I know.
You did it? Okay.
Yeah, let's see. That is
4.9 times
times
0.81 squared minus 4.9 times 0.8 squared equal divided by 0.01. 7.88 something. Okay, now, this time, do 4.9 times 0.805 squared minus 4.9 times 0.8 squared again. But divide that by 0.005. You get that? Okay. And if you keep doing that, the difference between these two, even squared, is going to be getting really, really small. But the difference between your T1 and T0 is getting really, really small. So both of those are getting to be small. numbers, but the ratio of them is actually seems to be going very close to 7.84. You can plug in these numbers and see that indeed it's getting very close to that. Okay. Now, okay. Now, I feel like cheating here. We all mind if I cheat a little bit? I'm going to jump ahead and actually do the calculus. Okay. You haven't had this yet, so don't expect to. I'm going to do ds dt. Where does that come from? It's just like delta s over delta t, but now it's going to be instantaneous. Now, you don't know this yet, but what that is 2 times 4.9, which is 9.8 times t. Your t here, that's common here, is 0.8. So 9.8 times 0.8, you tell me what that is. (9.8) times 0.8. 7.84. Look at that. What do we say this looks like it's getting closer and closer? It started off 7.89, 7.86, 7.8405, 024, 0005, and it kept getting slower, it's getting closer and closer to 7.84. And you do calculus, you got that. Like that. Okay. This is called taking a limit. You try numbers closer and closer and closer together and do the relationship, the ratio, and you hope to get some pattern developing, 7.84, and that's exactly what you get with calculus. Thank you, Isaac, for making it a lot easier. Now, let me back up just a little bit in history. Before Isaac Newton and Galileo, in fact, way before them, there was a guy, and you've probably heard of him before, named Archimedes. Buoyancy, Archimedes' principle. He was, 200 BC, way before them. They were in 1800s. So basically pretty close to 2,000 years before Newton. Pretty close to that was this guy named Archimedes. He didn't have all these tools and stuff, but guess what he did? Now, here was his problem. He wanted to know how to get the area of a circle. That's a hard thing to get. The area, can't write on that. Okay, the area of a circle. I shouldn't be taking time to do that. That's not a very pretty circle. But what he started doing was taking shapes that he could take an area for, like an equilateral triangle, and putting one on the outside and one on the inside, equilateral triangle. He could calculate the area of an equilateral triangle. No sweat. And he could have this on one on the outside. No sweat. And then something in between that would be the area of a circle. Sweat, okay? It's hard to get the area of a circle. There's no exact formula that had been developed at that time. Well, that worked okay, but there's a lot of error there. So rather than the area of a circle, he went to the area of a square. And you see, if you take a square and put it inside of a circle, that's not a very pretty square, it's not a very pretty circle. And do one on the outside of the circle, it should touch each side. That's a lot better approximation. And you can do, there is a formula for the area of a square, both on the inside and outside. Well, if that works so well, then why not do a 5-sided figure? Okay? That's a pentagon, a regular pentagon. And Archimedes did this too. And I can't draw these very well, so I'm going to do my best. This is ugly. That's 6, isn't it? I didn't do it very well. But guess what? He went on and did 6. Because there is area for a pentagon, for a hexagon, for an octagon, for or a decadon, you know, and he kept getting bigger and bigger. But you see right here, no, that's 5. That's the pentagon. And then he did one on the outside of the circle. Whoops. That's not very pretty. But you see they're getting closer and closer and closer. And believe me, to do them, that's not an easy thing either. He could do it. He was bright. He was really bright. And he did this. And then he did more and more sided figures, 18 sides, 20 sides. I don't know how far he went, but he was getting closer and closer on the inside and closer on the outside, and he knew the circle was somewhere in between. When he got up to a certain precision, you know what method he called this? The method of exhaustion. Yeah. He said, this is getting so hard. At some point here, I'm going to say, that's close enough. I'll say that's the area of the circle. May not be exact, but it's close enough for government work. Okay? And that's what he did. He called it the method of exhaustion. What he was doing was taking the limit. What Newton did, by taking numbers closer and closer to each other, he was taking the limit. Okay? Leibniz did it. These were limits. And this is why we study it. So let's do example 1. We just did example 1, didn't we? A hammer falls off of scaffolding at time t equals 0. Estimate the instantaneous velocity at time t equal 0.8. We just did it. These are, when you use 0.81 minus 0.8 over 0.01, we just did it. Using Galileo's formula he came up with, and we found as you get closer and closer to 0.8, and all these times you're getting closer and closer to it, you're getting closer and closer to 7.84. That is the instantaneous velocity. Okay? And sure, that's meters per second. Okay? So, sorry, I should have read that was example 1. What we're getting down to, or up to, okay. Now this is not quite where we were a while ago, but it looks awfully close. Same formula. This is what we call the slope of a secant line. Now they left off a block here. The average velocity converges to the instantaneous velocity if you get smaller and smaller increments there. Instantaneous velocity is the limit of the average velocity as the length of the time interval shrinks to 0. The length of the time interval shrinking to 0. I should have done this before I got there, but I'm going to write it on this slide. So let me write it here. The instantaneous velocity is equal to the limit as delta t approaches 0 of the average velocity. Okay. And what was the average velocity? Delta s over delta t. Remember, that was what we defined average velocity to. But do you see a problem with this concept? Huh? Okay, I couldn't hear. Oh, the limit as delta t approaches 0 of the average velocity was delta s over delta t. Now, can you see a problem with this? Delta t, in all the math we've ever done in our lives, we've been told, what can you never do? Yes, you cannot divide by 0. We've heard that your whole life, right? But guess what you're doing? You're letting delta t get close to 0. That's what we did in that last table. The delta t was going from 0.01 to 0.005, 0.001, 0.00001. You know, it was getting closer and closer to 0, and you could see the ratio was getting closer and closer to a number. But you can't put a delta. You can't put a 0 down there in the number. can you? Well, here's something that limits do, okay? And the book doesn't go into this. Back when I took calculus, to me that this made a lot more sense. So that's why I'm going to tell you. If n is a number, n divided by 0 is undefined. You can't do it at all. If n is a number such as 7, 3/5, 0.4, you can't ever divide that by 0. Undefined, you can't do it. However, 0 over 0, that's called an indeterminate form. You don't say you can't do it. You really can't divide anything by 0. But if the numerator and both the denominator are both going towards 0, that doesn't mean it can't happen. Okay, yeah. You get closer and closer. That's an indeterminate form. And that's what limits do. They tell you whether the indeterminate form actually has a limit or not. Okay? This will never have a limit. 7 over 0 is not going to have any value at all. But it may be, and that's what we saw before, the distance that it traveled between 0.8 and 0.80001 is getting closer and closer to 7.84. That limit does exist because that's an indeterminate form. Some indeterminate forms will not exist, others will. That's what we're dealing with. Okay? So, they're introducing this concept of a secant line. They give you this formula before you tell you what it is. Let's see if they have a slide. Yeah, here's one. Okay. Here is a guy, his displacement on his bicycle. He's driving uphill, it looks like. Okay. He's driving on his bicycle, riding on his bicycle. T equals 0, he's here. A little bit later, he's here, and then he's there, then he's there, then he's there, then he's there, and then he's there. At T equals T1, he's there. Now, if you said what was his average speed, it's how far he was at T1, that's S of T1, minus how far he is at S of T0, that's your slope of that secant line. The secant line is the line that cuts a curve in two places. That's the secant line. Okay. Now, if you let this T1 here get closer to T0, you see if you let that be like here, then the slope's a little bit less. If you let it be here, it's a little bit less. Here, a little bit less. And somewhere down here, at some point here, the slope of that secant line, as you let the delta T get smaller and smaller and smaller, the limit of that would be the slope of the tangent line at that point. There is the key. Because that's an indeterminate form, as you let the delta T get smaller and smaller, your delta S is also getting smaller and smaller until your change of S and change of T is both approaching 0. But that indeterminate form has a limit, and that's going to be the slope of this tangent line at the point T0. Okay? So that's what we're meaning, and why did I blow this one up? I don't know. That's what we mean by a secant line. It's a line that connects, that intersects a curve at 2 points, and then as you let the delta T on the horizontal axis get smaller and smaller and smaller, by definition, your delta S is getting smaller too, but if it does have a limit, this is the slope of the secant line. That's your average speed between these 2 points. But if you let that second point get closer and closer, then you're getting closer and closer to the tangent line, which is the instantaneous speed, the slope of the tangent line. Okay, so that's why they say back here, the average velocity is the slope of the secant line, delta S over delta T. That's delta S. Same as we had before, S of T1 minus S of T0 divided divided by T1 minus T0. Change of S with change of T. Change of Y with change of X. Slope of that secant line. But as you let the delta T get closer and closer to 0, the delta S is also getting closer and closer to 0. Then you have an indeterminate form getting toward that. And if that has a limit, that is your instantaneous speed. Okay? Is that making any sense? Okay. Here is a picture that shows that with different secant lines. Okay? Same picture as we had before. It just doesn't show the guy biking uphill, straight up. Okay? It started here. In fact, this is the hammer drop again. Same one we had before. This was the difference between 0.8 and 0.805. I think that was the second we did. That was the slope of that. Then we did between 0.8 and 0.8001. That was that slope. Then we did the 1, 8, and 0.80005. That was that slope. And look at that. They're getting closer and closer to the actual slope of the tangent line. As the delta T goes to 0, your delta S is also going to 0, giving you an indeterminate form, and that ratio is going to approach the slope of the tangent line at T equals 0.8. This just takes those three entries out of that same table we had. These are the last three. They didn't do the first and the last three, but you could do it even closer. 0.80001. That would be right here somewhere. And then do it again. Every time you're getting that blue line, the slope is getting closer and closer to the slope of the tangent line. That's what you get when the delta T approaches 0, gets close to 0. S is also getting close to 0. That ratio of those indeterminate forms, that gives you your instantaneous speed at that time. Okay? Does that make sense? Okay. Before we leave this, there's a little blurb here that says, I'm going to write it down this time, I didn't the last time. Instantaneous velocity, okay, and it is equal to the slope of the tangent line to the graph okay, of position as a function of time. You probably can't read my writing, but it's in the book, so read it from the book. Okay. So I think we're ready for example 2. Except I don't see that being example 2. In fact, I don't see that as being any of the examples here. I think this must have been, see, the slide set I have is from the previous edition. So we don't have that previous edition anymore, so let's do example 2. Okay? All right. Sort of ignore that table there. I'm going to try to draw, and it says for you to describe the motion and velocities of a shuttle train that runs on a straight track at the airport. You've seen these before. You have a terminal here and the thing here, and you take the train, it goes on a straight track between that. So describe the motion and velocities of that shuttle train that runs on the straight track at the airport, ferrying passengers from one terminal to another according to the graph given here. Okay? Okay. Time t equals 0 is here at 0.0. Okay? Then it goes up, flattens out, comes down. Okay. and this is t equal 9. So this is your time axis. Okay, here's the position axis, and this will be measured in x. I don't know why they didn't use s like we did before. It doesn't matter. You can name it anything you want to. The maximum it reaches here is 800 watt meters. This x is in meters. So, and this time is measured in minutes. Okay, so 9 minutes it makes one complete cycle. Okay, now I didn't draw mine too well. I'll try to improve on this a little bit. This up here is actually exactly straight. So this is going to be 4 and 5 minutes. So it says describe this. What's the speed of this shuttle at time t equals 0? 0. It's starting from rest. Anytime something starts from rest, its velocity is 0. The slope here is 0. But it begins rolling, and as soon as it starts rolling, it now has a speed that's not 0. So it's a pretty slow process here. Where does it look like, just judging from my thing here, if this is 4 minutes, that would be 2, this would be 1 and 3. Where would it seem to be going the fastest? Somewhere right about in there, that's where the slope is greatest. See, it starts at 0, increases speed greater. And as fast as it's going to go, it now starts decreasing again and stops between 4 and 5 minutes. Yeah, it's got to let the people off and the new people on, but then it goes right back to the other one. So now it's going in the opposite direction. It has a negative velocity. It's going backwards. And those things do. They go like this and then like this. Then like this and like this. Okay? Going forward here, stops at 0 speed here, then I'm going backwards and pulls it at where it started from, slows down and stops and lets the passengers off there. So it goes right back to where it was to begin with. So it's back at position 0 9 minutes later. Yeah, that's pretty much how these things do. They go from one to another. Maximum speed forward is here, maximum speed back is here. Starts off at 0, increases slowly. After the maximum speed, decreases slowly until it goes to 0. Then increases going backwards, slightly negative, until its maximum speed about here, and then slows down, going backwards until it reaches 0 there. Okay? Yeah. That's a graph of a shuttle just going back and forth and back and forth. Okay? Notice several things. Velocities can be positive if the slope is positive, negative if the slope's negative. 0 if it's stopped, like where it dropped off passengers there. Okay. So I think that's what they wanted you to do or say or deal with. Now, they talk about other rates of change. Velocity is, and by the way, let me just see. Okay, there's a graph coming up for example 3. Okay, this is kind of bizarre here. Okay, all right, other rates of change. Velocity is only one of many examples of rates of change. Our reasoning applies to any quantity y that depends on some other variable x. Okay, let's just say, this should look familiar, y is equal to f of x. Okay, x is called the independent variable, y is the dependent variable. Anytime you can express something like this, you can then say, how is y changing if x is changing? In other words, what's the rate of change of y per change of x? That's a rate too. It could be how many miles you get per gallon of gas that you burn. You figure that. Or I do, because I like to keep that small. I mean, big. More miles per gallon, okay? You also talk about things like physics, if I put a flame under one end of a rod, we talk about how fast the heat travels down the rod. That's change of temperature per change of time. If it's got time in there, usually it's called the rate. Otherwise, it's called, it could be called rate, but you could have how does heat change as you go through different materials. What if you had a material that was 90% iron and you're adding more and more of something else to it, and it becomes 10% iron by here and 90% something else, copper or whatever you're going to mix with iron, then it may have a different temperature gradient, you might say. So yeah, you can talk about Y as a function of composition, temperature is a function of resistance, okay? You could have anything in there that you have changes happening as you change one variable, you're changing the other, okay? So when you have this kind of form, what your delta F then would be F of x1 minus F of x0. Now you could call it 2 and 1. I don't care what you call it. They call it this. So what would be the average rate of change? Do that over delta x, which would be x1 minus x0. So in other words, how is your function changing as you change your variable, the independent variable? This is called df dx, or change of f over change of x. Whatever rate those would be, okay? Now, the example 3 is similar to what the tables are here. So I'm going to erase this. I say similar, it's a different example. I don't have the old book here, or out here, so I can't tell you what the old one's doing. But example 3 in your text, if you got the new text, all of you have it, okay. Last term I had one person who had an old text and one who had a new, so I was last time I taught this. Okay. Suppose this formula B, and that B is number of bacteria, is equal to 5 times the square root of your temperature. That yields a good approximation to the amount of bacteria B as measured by its weight, so that would be weight of bacteria, that grows in a particular petri dish in milligrams. So that would be, it's really not weight, it's mass. Milligrams measures mass, not weight. We'll let them get away with this. This is a math book, not a physics book. Over 1 day as a function of the temperature in degrees Celsius. Centigrade. Should be Celsius. Can we relate that to something real? Okay, just about a month or so ago, I bet you ate a lot of food, didn't you? Did y'all have turkey for Christmas, or ham, or what? Ham? Okay. Doesn't matter what you have. Let's say you took it out, you carved it, and it sat there on the table. You all ate as much as you could. It sat there, you sat around the table and talked, you opened presents, you did whatever you did, you sang, whatever you did. You read, whatever you did, but you left that food out. Okay? Now, if that was out in the garage, and let's imagine that maybe Christmas Day was cool, then the number of bacteria growing in that ham was growing at a rate of 5 times the square root of your temperature. Now, we'll put that in Kelvin. No, Celsius. They said Celsius. So you know it's not below 0 there. If it were at 0, guess what? It's frozen. And at frozen, basically this is 0, so the number of bacteria is not increasing very much. Okay? But if that temperature were 5 degrees Celsius, centigrade, square root of 5 is a number around 2.1, 2, or 3, something like that. times 5, so in an hour, was it an hour or a day? A day. A day, you'd have a lot more bacteria. And if that temperature, if that was inside at 70 degrees, let's make it 20 degrees Celsius. Square root of 20 is 4 point something, okay? Probably around 4.5. 4.5 times 5 is going to be a lot bigger number of bacteria at the end of that day. Ooh, I don't feel so good, Mom. I ate some of that ham for midnight snack. Okay?
I'm trying to think of how many bacteria would actually be in 1 milligram.
Oh, boy. Enormous numbers, okay? Okay, that's what we're talking about here. That yields a good approximation to the amount of bacteria measured by its mass in milligrams in a particular petri dish, not your ham, but a petri dish, over 1 day as a function of the temperature in degrees Celsius or centigrade. And this only works for 0 less than or equal to T is less than or equal to 25. Okay? So that number, square root of T, will be going from 0 to 5. Okay? If you get much hotter than that, you might start killing some of the bacteria. So it won't work. This will be a normal rate at which they're going to increase pretty fast. Okay? Estimate the instantaneous rate of change of B with respect to T, mass of bacteria with respect to temperature in degrees Celsius when T is equal to 10 degrees. So we're going to take T equal 10. That's certainly within that domain. Okay, so we can do that. And it says estimate the instantaneous rate of change with respect to temperature when T is equal to 10. Okay? And what are the units for the rate? Milligrams per degree Celsius or centigrade. Okay? That answers that question. So how are we going to do this? Yeah, there's 2 ways. Okay? We could either let the temperature be approaching 10 from the low side, or we could let the temperature be approaching 10 from the high side. It's going to give us slightly different answers until you let that limit get closer and closer to the temperature get closer and closer to 10, so your delta T is getting closer and closer to 0. Okay? So let's do, and rather than these, we're going to say from 9.5, this is on the low side, 9.5 to 10. Then we'll do 9.8 to 10. Then we'll do 9.9 to 10. And then we'll do 9.99 to 10. Okay. So we're going to use those. That's going to produce different rates of change too. Let's see what we get. Okay. Here's our formula for B. Okay. So you're going to do, what your formula is going to be is the average rate of change, which is delta B over delta T. Okay. And you're going to have 5 times the square root of T1 minus 5 times the square root of T2, or T0 and T1. I don't care which way you do it. Let me make it so it's more readable. Okay. It doesn't really matter which you do. The book usually does this, so I'll try to do it. Over, all right, I did them backwards. 1 minus 0. Actually, almost would work better the other way, but we'll do it. Okay, 1 minus 0. And this will be T1 minus T0. Okay, now, Got your calculators? Pretty easy to do. 5 times the square root of 10 minus 5 times the square root of 9.5 equal, divide that by 0.5. 5 times the square root of 10 minus 5 times the square root of 9.5 equal, if that subtraction equal, divided by 0.5. Did you get that? That's what the book got, so I don't know. Have you tried it? Say again?
I said I'm getting there.
Okay.
My calculators.
These calculators really slow you down, don't they? Did anyone get that? Something close to it. 5 times the square root of 10.
There we go. Yes, I finally got it.
You got it?
0.8000707.
We'll stop at 4 digits. Okay? Now do it with 5 times the square root of 10 minus 5 times the square root of 9.8. That difference is going to be a smaller number. But you're dividing it also by a smaller number, 0.02.
0.7945.
0.7945?
0.7946 if you round up.
7946. What did the book get? Good for them. They got it too. Okay? Let's go to a tenth of a degree difference. 5 times square root of 10 minus 5 times the square root of 9.9. It's going to be a really small number. Divided by 0.1.
0.7926.
0.7926. Okay? Can't see that we got a limit yet. Let's keep going. The 5 times the square root of 10 minus 5 times the square root of 9.99. It's going to be a really small number. Divided by 0.01.
0.7908.
0.7908.
Setting it up half the problem, and then, or really the whole thing, then you just go and plug in.
Right, exactly. Okay, now, it kind of looks like 0.79, something pretty close to 0.79. Might be the limit. Okay, let's do it the other way, though. Let's get close to 10 from the upper side. This is called the left-hand interval because you're going approaching 10 from the left. Let's approach 10 from the right. So then what you're going to have is the lower limit's going to be your 10, and your upper limit's going to be 10.5. Then it's going to be 10 to 10.2. Then it's going to be 10 to 10.1. And then it's going to be 10 to 10.01. Okay? I should have done this in a different color, shouldn't I? What color you want? Blue.
Green.
You want light blue, light green, dark green?
Dark green.
Dark green, okay. So this will be dark green. I'll put our answers over here in dark green. Okay? So what we'll do is 5 times the square root of 10.5 minus 5 times the square root of 10 divided by 0.5.
I got 0.7809.
7809. Okay? Now let's do 5 times the square root of, 5 times the square root of 10.2 minus 5 times the square root of 10 will be a smaller number divided by 0.2, which is also a smaller number.
0.7867.
Okay, so it's getting closer to what we were heading before. Okay, let's now do 5 times the square root of 10.1 minus 5 times the square root of 10. Again, going to be a smaller difference, but your denominator is also smaller, divided by 0.1.
0.7887.
0.7886. Okay? Now let's do 5 times the square root of 10.01 minus 5 times the square root of 10 equal divided by 0.01.
0.7904.
Okay? We approached it from the left and we're getting close to 0.908. Approaching from the right, it's getting close to 0.7904. I'm going to guess the real answer is somewhere close to 0.97906. Here's my guess. What color do you want my guess to be? Have a preference?
I'm sorry.
What color do you want my guess to be?
How about light blue?
Light blue. Okay? My guess is 0.7906. Okay? Now, you want me to cheat and tell you what the real answer is? Okay. If this is your B, now I'm going to rewrite that slightly. I'm going to write that as 5 times t to the, what the square root, what exponent would that be? Square root is the same as exponent 1/2, right? Square root is, see the 1 is the exponent inside, and the denominator is the index of the radical. Since it's the square root, that's a 2 there. So that's 1 over 2. Okay? Now, y'all don't know this yet. You're not supposed to know yet. Pretend I'm not doing it, okay? But I'll tell you what it is. It's 1/2 of 5, which is 2.5, times t to the minus 1/2. So this will be 2.5 over the square root of 10. So if you'll take your calculator and do 2.5 divided by the square root of 10. If your calculator won't do it, I will rationalize with the denominator, but it will do it right. 0.7906. Oh, why did I not change my colors back? Look at that. Look at that. Exactly what we guessed. Okay. Good deal. Y'all don't worry about that last part. That's what a derivative does for you. I'm sorry, you don't even know that word yet. Pretend I didn't say it. Okay. All right. Now, what this was doing, and the units are milligrams per degree Celsius. They say centigrade, but capital C is Celsius. What's wrong with them? Okay. What that's actually doing, and there was the right-hand interval. I just wrote it on the other page. Okay. Now, this is not, well, it is. Oh. The graphs look very similar. The reason for this is they did temperature in Kelvin, which is what they should have been doing. That formula really doesn't work for Celsius, but they were using that, but they're doing it for Kelvin. And you see it's not quite the same, but it's very similar. Oh no, but this is V in meters per second. So forget that. But the graph's very similar, okay? Not quite the same, but similar. This is the real function here, okay? This is, and they don't give what it is. And their slopes are different. But our function looked very close. And when you did the secants from the left-hand side, there was the first one, that was its slope. The next one was here, the next one there. Closer they get to we were going to 10 Celsius, they were going to 273 Kelvin, then it's getting close to that tangent line. When they did the slopes from the upper side, then these were all too low. Here's a slope from that one, that one, that one. And again, it's approaching the slope. Our numbers trend is the same. From the lower side, they overshot coming down closer. From the upper side, they undershot, and we're getting closer as close as you get. Same thing that happened here. The figures look similar. The functions are just a little different. Okay. To conclude the section, we recall an important point. I've already mentioned this to you, discussed in 1.2, which was review of pre-calculus. We didn't do that. By the way, did anyone go over it and find anything they really needed to review on? Always look if you need to. This was back there in that first chapter. For any linear function, f of x, it's a linear function. Let me go back to dark anyway here, purple, okay? A linear function, f of x, is equal to mx plus b. That's a linear function written in slope-intercept form, okay? The average rate of change over an interval is equal to the slope of the function. Now, how do we verify that? What this means, delta f over delta x, that's the change of the function per change of your independent variable, that would be f of x1 minus f of x0 divided by x1, x1 minus x0. And we don't even have to put numbers in there. We can just do it generically. F of x1 would be m x1 plus b, right? Minus f of x0 would be m x0 plus b, right? Divide that by x, I'll do it again, x1 minus x0. Okay. Now the m's the same. This is a straight line. It doesn't change no matter where you are. Okay? Well, guess what? Oh, well, should have put parentheses there. You could put them in front too, but it's not going to make any difference. So let's clean that up a little bit. That would be m x1 plus b minus m x0 minus b. I'll distribute the minus sign across. x1 minus x0. Okay? Well, guess what? Plus b minus b, they disappear. Well, now we got the same thing here. mx1 minus mx0. You can factor out the m and leave x1 minus x0 divided by x1 minus x0. They go out. The slope is m. It's the same everywhere because it's a straight line. The slope. So if you're going on cruise control at constant speed, that is your instantaneous speed. It's always the same, okay, if you have a linear function. The ratio delta F to delta X is equal to M. All right. Now, I think that does it for section 2.1. Okay. Now, for those who may have had Ms. Martin before, I think she liked the summaries at the end of each section. I would suggest go over them. It summarizes what we just covered. Well worth it. What I kind of like, I don't know if she uses it or not, the preliminary questions. Do you find, well, you probably haven't used the book before, but did she do those? Okay.
I mean, really, with you, it's only, whenever, yeah.
What's that? The exercises? Okay. So you've had her before too? For calculus or? Okay. All right. So she just went to the exercise. I like to do the preliminary questions, sort of get you thinking, then I assign the exercises. Then if you can't do those, come back and we'll go over those. I usually assign the odd number exercises. Why? Because the odd number have answers in the back. Okay? But the preliminary questions, all those answers are in the, well, sometimes they're in the back. Okay? So I'm going to clear this out of the way. And to keep from having to go to a new thing, we'll just write around this. Average velocity is equal to the slope of a secant line through 2 points on the graph. Which graph? That's a rather strange question. Average velocity is equal to the slope of a secant line through 2 points on a graph. Which graph? I'm not even absolutely certain what they're talking about. I'm going to express it this way.
Oh, on a curve.
Yes.
So I guess a parabola?
It could be a parabola, it could be any curve whatsoever. So if this is 2 points on that graph, let's call that graph y is equal to f of x. Okay? Whatever it is, this is the graph of f of x. Okay? And you do the secant line, that's the average speed or average change of your f. This is your y, which is f of x. So this is the change of y or change of f, whichever you want to call it. This is your change of x, delta x. So the rise over run, delta y over delta x, that's the slope of your secant line. So I would say the function. I don't know what they're looking for. Which graph? Let's see if we can find this in the back. This is 2.1 preliminary question. To me, it's a really vague question. So 2.1, the graph of position as a function of time. If that's what you were measuring, fine. If that's the graph, okay. Oh, if you're talking about average velocity, I wasn't paying attention to what average. I was saying average value. Average velocity, then that would be position. This would be position over time. So not x, but t. Because if you're talking average velocity, because the units of position over time, that would have to be change of position over change of time. Okay, that's what we meant. Number 2, can instantaneous velocity be defined as a ratio? The average velocity, for sure. Change of position over change of time, that's a ratio. Instantaneous velocity, though, generally is the limit of a ratio, which technically that becomes 0 over 0. So yeah, we usually don't use that. If not, how is it computed? It's computed as a limit. That's what, at least what I think the answer should be. Let's see what they say. No, instantaneous velocity is defined as a limit of the average velocity as the time elapsed shrinks to 0. So average velocity can be expressed as a ratio, but instantaneous is the limit of those ratios as your delta t goes to 0, which would then be a 0 over 0 indeterminate form, which technically you can't divide by 0, so we don't do it. Okay, number 3. What is the graphical interpretation of instantaneous velocity at a specific time t equal t0? What is the graphical interpretation of the instantaneous velocity there? Well, if this is t0 here, what is the graphical interpretation of that instantaneous velocity at t equal t0? Say again? The graphical representation. I'll give you a hint. The average velocity is represented by the slope of the secant line. What is it represented the instantaneous velocity? Slope of the tangent line. I'll do that in red. Because they tend, whoa, I thought I was going to do it in red.
That was a weird roundabout way of saying it, but I understand it now.
Yeah, it truly is. It's not going to give me red. Let me do green. Okay. Yeah, the slope of the tangent line. If the average velocity is defined as the slope of the secant line between the 2 points, the instantaneous velocity is the slope of the tangent line at that point. Now that's what I think it should be. Let's see what the back says. The slope of the tangent line tangent to the graph at that position, t equals t0. Very good. Number 4, find the graphical interpretation of the following statement. The average rate of change, I think I'll write this down. So let me go back to dark and clear my slide. Okay. All right. Find the graphical interpretation of the following statement. The average rate of change approaches the instantaneous rate of change as the interval x0 to x1 shrinks to x0. I don't think I need any. Wish I'd have left the last one up there. Find the graphical interpretation of that statement. Let's just pretend I have that last one up there. Here's the curve between here and here. There's the secant line. This is x0. This is x1. The graphical interpretation of that statement. The average rate of change approaches the instantaneous rate of change as the interval x0, x1 shrinks to x0. Well, that then would be to there, to there, to there, and ultimately we're going down to there. But it didn't take. Yeah. So I think this is what they mean. Find the graphical interpretation of the following statement. The average rate of change approaches the instantaneous rate of change as the interval x0 to x1 shrinks to x0. Okay, what that means is your slope of your secant lines are getting closer and closer to the slope of the tangent line as x1 gets closer and closer to x0. It seems like that's the same thing we've been saying over and over and over. Maybe that's the point. Let's see what they say. The slope of the secant line over the interval x0 to x1 approaches the slope of the tangent line. That's exactly the same. Okay, number 5. The rate of change of atmospheric temperature with respect to altitude is equal to the slope of the tangent line to a graph. Which graph? And what are possible units for that rate? Well, this one, I think I will erase and go back to a dark color. Okay. The rate of change of atmospheric temperature with respect to altitude. I'm going to write this out. The rate of change. How are we doing on time? Ooh, so close. Okay. Of atmospheric temperature with respect to altitude, RWT, with respect to altitude, I abbreviate everything, is equal to the slope of the tangent line to a graph. Okay? Which graph? Okay, that's the question. Guess what? It's all hidden in that first statement. That's why I put it down. The rate of change of atmospheric temperature with respect to altitude. The atmospheric temperature is the vertical and altitude is the horizontal. This with respect to that is the slope of the tangent line of the graph. What is the graph? It is the graph of temperature as a function of altitude. So you have altitude going this way, temperature going that way, and I can't think what that looks like. It's a rather strange curve, really. It does all sorts of weird things in there, but that is the slope. Actually, I would say in general temperature is decreasing with respect to, because up there it's even colder. So anyway, that's the slope, and then it says what possible units for that rate. come up with some possible units for the rate. Say again? I can't hear. Say again? Yeah, altitude is the vertical, and temperature is vertical, altitude is horizontal. So that could be degrees Fahrenheit per foot, degrees Celsius per meter, Kelvin per kilometer. I mean, it could be anything as long as you have temperature on the numerator, altitude, which would be how high it is. It may even be in miles. Okay? Let's see how they answer it.
First I thought it was trying to get us to set up like an equation almost like,
No. Yeah.
with respect of, temperature,
Yeah, but it's just this graph. The graph of atmospheric temperature as a function of altitude. Okay? Possible units would be degrees Fahrenheit per foot or degrees Celsius per meter. I can't believe I said the same. To say that.
Yeah.
Okay.
If they said the Kelvin, if they actually said all the
Or
numbers,
Kelvin.
yeah.
Yeah. Okay. Now, homework exercises. I would do some of the either 1 or 3 or both, because the answers are in the back for the odds. I would do number 5. It's the only one sort of like that. Then do either 7 or 9 or both. This is beginning on page 60, going to 61, 62, and maybe even top of 63. Then I would do any of the odds 11 through 17. Then do any of the odds 19 through 31. Any of the odds 19 through 31. I'll let you choose either which ones you're interested in, which ones look like they'll be fun to you, or which ones might be a little hard. See if you can figure those out. If you can do the harder ones, you can probably do the easier ones. So I'll let you decide which ones you want to do. Okay? And these are just for your practice because the test, and we did talk about maybe having take-home tests. The test will be similar to the homework questions. I guarantee you, though, they have a really lousy test bank. I try to find the ones that are most similar, but sometimes I can't get them too close. But if you do these, you have the best chance of doing well on the test. We'll begin next time with 2.2 limits, numerical and graphical approach. It feels like we've already been doing that, but we'll continue doing it. All right. Any questions? We'll see you on Monday. Hey, we'll actually have class on Monday the next week. Amazing. Haven't had them before. Okay. Oh, good deal. Thank you. Yeah. What indicated here is at the time I printed this off, you have to take that. Have you? Okay, no. If you have, you're in good shape. I was going to say they said they were going to remove all non-paid students from the roll as of last evening. So I wanted you to check if that was the case. But if you had already paid,
yeah, of course.
made it. Yeah.
Okay, this is what she came up with.
Oh, this is your schedule?
Okay.
And did you finish that? I mean, have you completed registration?
Yeah, she
You did? Okay.
completed.
Okay, good. I
What I
mean,
want to know is it everything that I need to take to graduate this semester?
oh, you want me to look at the degree plan?
And then we're trying to work out.
Okay, I think I made most of these marks. Okay, someone really messed up here. Okay. You need calculus 1, you're taking that now. Good deal. You've got those done. You got 2 histories, so are you taking?
I took psychology already.
Sociology. Fantastic. Okay. And down here, pre-professional electives. You're doing physics 202 as your pre-professional elective.
I was doing this because those are my degree plans later on.
Yeah, exactly. So, is that going to give you enough hours?
This one I was trying to shoot. What she said? She said this is all I needed to graduate from this.
Okay, who's she?
Chisel.
Okay, Miss Chisholm. Okay, is if she said it, it's fine. Okay, because that would give you, with 4 hours here, that would give you, you got 11 and 4.
I was just trying to see how she added that up. I don't know if she
With 15. Where is she coming up with?
She said I had an extra. Oh, it's in this. My math 100.
Oh, she was counting some of those. Fantastic. If she counted them, that looks good to me. Okay. So have you done the notification? Well, I should have turned this off.